My dear students, in this video, I am going to define total probability and Bayes theorem. We are going to see what is total probability. On the definition of total probability, we are going to define Bayes theorem. Consider S is the sample space. This S is the sample space. The sample space is consisting of the event E1, E2, E3, E4, etc. En or n disjoint and exhaustive events of the sample spaces. The events E1, E2, E3, E4, etc. En exhaust the sample spaces and are disjoints also. Let A be any event. Let A be any event associated with the sample spaces. Then the total probability states that probability of A equal to probability of E1 into probability of A by E1 plus probability of E2 into probability of A by E2 plus etc. Conditional probability. I mean probability of E1 into conditional probability of E1 plus probability of E2 into probability of event A occur that the event E2 is already occurred. Like that, probability of En equal to P into A by En. This is the total probability of the event A. That is equal to sigma j equal to 1 to n. The summation of these probabilities, the total probability of the event A is sigma j equal to 1 to n. Probability of E of j into P of A by Ej. The probability of event A, given that the event Ej occur already, where j equal to 1 to etc. This is the total probability of the event A. This is what we have to prove. For that, proof. Given that E1, E2, E3, etc. E1, etc. En are n disjoint events and they exhaust the sample spaces. Okay. Disjoint and exhaustive events of the sample spaces. That is S equal to E1 union E2 union E3 union E4 etc. En. The union of all these n events constitute the sample space S. Now we know that EA intersection EJ, E1 intersection E2. See, E1 and E2 are disjoint. Therefore E1 intersection E2 is 5. Similarly, E2 intersection E3 is 5. MJ. Therefore, generally I have defined that EA intersection EJ equal to 5, where I not equal to J, E1 intersection E2, E2 intersection E3 and so on. In general, EA intersection EJ equal to 5, where I not equal to J, where I and J are 1 to etc. n. Then for any event A, in the sample space, yes, this is A is the event A is the intersection of A and the sample space. Yes. A is the event such that A equal to A intersection of S. Okay. Now the any event A is A intersection sample space S is A intersection of the sample space S is A itself. That is, therefore, A equal to the event A equal to A intersection S. A intersection S, you know, S is E1 union E2 union E3 union etc. union En, you know. This is S is replaced by E1 union etc. En. This is again by associative law. This is A intersection E1, A intersection E1 union A intersection E2, A intersection E1 union A intersection E2 union A intersection E3 union etc. union A intersection En. This is by associative law. Now A intersection E1, this part. and A intersection E2 are mutually exclusive. Therefore, probability of A equal to probability of A intersection E1 union A intersection E2 union A intersection E3 etc. union A intersection En. This is equal to, since A intersection E1, A intersection E2, A intersection E3 and so on, A intersection En are mutually exclusive, therefore probability of A is defined by, these are mutually exclusive even, therefore probability of A intersection E1 plus probability of A intersection E2 plus probability of A intersection E3 plus etc. plus probability of A intersection En. This is by these events are mutually exclusive, therefore some union of the probabilities of the n events is addition of just probabilities of events. Probability of A equal to probability of A intersection E1 plus A intersection E2 plus probability of A intersection E3 and so on. Now by multiplication theorem, we know that by multiplication theorem, we know that what is that? P of probability of A by E1 equal to probability of A intersection E1 by probability of E1 no. This is by multiplication theorem, probability of A intersection E1 equal to P of E1 into P of A by E1. This is on multiplication, you get probability of E1 into probability of A by E1. So this is multiplication theorem, we know that. So probability of A equal to probability of A intersection E1 is P of E1 into P of A by E1. Probability of E1 into probability of A by E1 plus probability of A intersection E2 is probability of E2 into probability of A by E2 and so on. This is equal to, finally, probability of A intersection En is probability of En into probability of A by En. So this is again equal to sigma I equal to, J equal to 1 to N, J equal to 1 to N, P of Ej into probability of A by Ej, where J equal to 1 to N and probability of Ei is not equal to 0, where I equal to 1 to etc. N. Probability of all events are non-zero probabilities. The events E1, E2, etc. En has non-zero probabilities. Therefore, that's all about the total probability. Probability of A equal to sigma J is equal to 1 and P of Ej into probability of A by Ej. That's what we have to prove. This is the total probability of the event A. Okay? Now, by using the definition of total probability, I am going to define Bayes' theorem. Bayes' theorem statement is this: if E1, E2, E3, etc. En are n non-empty events which constitute the sample space S. The n disjoint events constitute the sample space S, and these are disjoint, pairwise disjoint. Therefore, E1 union E2 union E3 etc. union En equal to S. That you know, because E1, E2, E3 are pairwise disjoint units even and constitute a sample space S. Therefore, S equal to E1 union E2 union E3 etc. union En which we defined already in the total probability. Now, Bayes' theorem states that probability of the event, particular event, probability of the particular event EI, given that the event A has already occurred, because A is any event of non-zero probability. A is any event of non-zero probability. Now, Bayes' theorem states that probability of the event I such that the event A has already occurred equal to probability of EI into probability of A by EI. Probability of the event A such that the event EI is already occurred divided by the total probability P of A, that is sigma j is equal to 1 and P of Ej into P of A by Ej. This is the Bayes' theorem. By definition, we know that probability of EI by A is, by the definition of conditional probability, probability of EI such that the event A has already occurred is probability of A intersection EI by probability of A. Probability of EI by A is probability of A intersection EI by P of A. We know by multiplication theorem, probability of A intersection EI is probability of EI into probability of A given that the event EI is already occurred. P of EI into P of A by A, you know, divided by this P of A by total probability sigma j is equal to 1 to n probability of Ej into probability of the event A such that the event Ej has already occurred where I equal to 1 etc. Okay, so this is the probability of the event EI such that the event A has already occurred is P of EI into probability of A by EI divided by sigma j is equal to 1 to n probability of Ej into probability of the event A such that the event Ej has already occurred. So this, using this Bayes' theorem, I am going to solve one problem now. Okay? Now, see this problem. Using Bayes' theorem, we are going to solve this problem. Bag 1 contains 3 red and 4 black balls. And bag 2 contains 5 red and 6 black balls. One ball is drawn. One ball is drawn at random from bag, any one of the bag. And it is found to be a red ball. Find the probability that the ball drawn is from the bag 2. See, you have to draw a one ball from any one of the bag. That ball is red ball. Find the probability of drawing the red ball from the bag 2. What is the probability of drawing the red ball from bag 2? That is we have to find. See, bag 1, bag 2. Bag 1 contains how many red and black? Bag 1 contains 3 red, 4 black. Bag 2 contains 5 red and 6 black. This is bag 1 and this is bag 2. See, the total balls in the bag 1 is 7, in bag 2 is 11. Okay. Now, bag 1 containing 3 red and 4 black, bag 2 containing 5 red and 6 black balls. Our event A, let the event A is our required event. A red ball is drawn. Our event A is red ball is drawn from one of the pack. A is the event drawing a red ball. A is the event a red ball is drawn, or A is the event that is the drawing a red ball. What is the probability of choosing bag first? What is the probability of choosing bag 1? Probability of choosing bag 1 is, you consider, that is E1. Probability of choosing bag 1 is, you consider P of E1, that is equal to 1 by 2. Because 2 bags are there, choosing one bag is 1 by 2. Similarly, probability of choosing bag 2, that is P of E2, I consider. This is also 1 by 2. Probability of choosing bag 1 is 1 by 2 and probability of choosing bag 2 is 1 by 2. Because there are 2 bags, choosing one bag is probability 1 by 2. Now, probability of choosing a red ball from bag 1. What is that? Our idea is probability of choosing red ball. Now, probability of choosing a red ball from bag 1, that is probability of choosing red ball from bag 1 is P of A by E1, that is equal to probability of choosing red ball from bag 1 is how many red balls here? 3. Total balls 7, therefore this is 3 by 7. Probability of choosing red ball from bag 1 is 3 by 7. Similarly, probability of choosing red ball from bag 2 probability of choosing red ball from bag 2, that is probability of A by E2, second by probability of choosing a red ball. A is red ball, bag 2 from choosing the bag 2, that is there are 5 red balls in bag 2, therefore this is total balls 11, total I will. Now our question is we have to choose the red ball from bag 2. What is the probability of choosing the red ball from bag 2? That ball should be drawn from bag 2. That is, we are required probability of drawing red ball from bag 2. From bag 2. That is probability of E2 by A. So probability of choosing the red, first we have to choose the bag 2 and then we have to choose the red ball. In this case, we are choosing the red ball first and then already we are choosing the bag 2. See, P of A by E2 is probability of choosing the red ball, given that the bag E2 is already occurred. We are choosing the bag first and then we are choosing red ball. Here, we are choosing the red ball first and that red ball from E2, bag 2 we have to draw. So this is a Bayes theorem. This is probability of E1. What is it from bag 2? Is it not? So we have to find out that probability of E2 into P of A by E2. Probability of E2 probability of E2 into probability of A by E2 divided by total probability P of A, that is probability of E1 into probability of A by E1 plus probability of E2. Bayes theorem states the probability of E2 into probability of A by E2. That's our question. So probability of red ball choosing the bag 2 is probability of E2. What is probability of E2? 1 by 2. And the probability of red ball choosing the bag 2 is 5 by 11 divided by P of E1 1 by 2 into probability of red ball from the first bag is 3 by 7. Plus probability of choosing bag 2 is 1 by 2 into red ball from bag 2 is 5 by 11. Okay. On simplification, this is 5 by 22 divided by, what is that? 5 by 22. This is 3 by 14. Plus 5 by 22. By 22. Probability sign. So 14 and 22. LCM for 14 and 22 is 2, 7, 11, 77. Okay. 7 2s are 14, 11 2s are 22. $154. See, 14 and 11, 154. So, in this case, here I am going to write probability of E2 by A equal to 5 by 22 by 154, that is 22 into 3, that is 154, 11, 14 is 154. Yes, 11 3s are 33. Similarly, 7 22s are 154, 7 5s are 35. So that is equal to 5 by 22 into 154 by, this is 868. Again, 7 5s are 35 by 68. So this is the required probability. So probability of drawing red ball from back to is 35 by 68. That is the problem. See, after this step, you come here. This is probability of the drawing a red ball from back to is, probability of E2 by A is 35 by 68. That's all the problem. Okay. I will continue the remaining in the next video. Thank you.